Okay, so basically today we'll have a discussion on, just a moment, I'll just connect the meeting pad. So today we'll try to look into differential amplifier. Now what I'll do, I'll try to give you the schematic and an idea on its design, because I need to brief you about the theoretical aspect also about the differential amplifier. I'll try to cover up that maybe in the next session. Along with this, the cascode amplifier, why we use that, all those theory, as a brief overview of what exactly we do with the differential amplifier. But here, let me just give you the design overview, and then from here onwards, you can take it further and build on your own. Because this design and all, it is very similar, because we are using potential divider method. And when we use the potential divider method, it's more or less the same thing that usually we have done in our all the other amplifiers. We're going to divide the potential and we're going to consider the result. So basically, our differential amplifier. So if I just want to give you a simple overview of what exactly you do it in the differential amplifier is, you see, in the differential amplifier, you want to give in two inputs, and the output will just amplify the differences between the two inputs. So that is basically the main property of your differential amplifier. Then why you give the two inputs, and what's wrong in giving, or why we made it deliberately to give the two inputs. Basically, when we want to see this kind of amplifier are sometimes used in basically in most of the cases to eliminate the noise, and it will take the only the differences between the actual signal and it is going to eliminate the noise. And as I said, it is going to eliminate the noise. It sounds interesting, but we need to understand the theory behind it, how exactly it is going to look, and how the gain factor would look into the scenario. So when I say there are two inputs and it's going to eliminate the noise, there are multiple terms coming into the picture, like uh, slew rate. Then there will be CMMR, which usually you have come across in your op-amp, which is common mode rejection ratio. This is the rate at which the output changes with respect to the time, right? So all these things will come into picture. Now, how exactly it is going to do that? It's a theory behind that. Let's not get into the theory. I'll just put it a little bit upside. Now let's get into the schematic, and let us quickly get into the designs of this, so that once we know how the circuit works, understanding the theory behind that will be very easy. So that's what I just believe. Let's try to first get into the schematic. Now here is how your differential amplifier schematic looks. So you have your VDD, which is connected. I'm taking here it as 1.8 volts. So I'm considering four MOSFETs, out of which you have your M1, where you are going to give the input number 1. Then you have, these are your NMOSes. This is your M2. We are going to give the input number 2. you have M naught, where you're going to give something called as a tail current. Here, instead of we use the term ISS, but nevertheless, it can be also termed by the name IDD also. So that's your VG0. Okay. Now this is M1, M2, M3, M4. The upper things are your PMOS, which is going to act as a load. And this is in this diode connected format. And the belows are your two differential amplifier schematic. From here, you're going to take the output. Now, this is a single-ended output. You're not going to consider the differential output. You're going to consider the output only from the one particular terminal. And there are differential amplifier where you want to take the multiple outputs at both ends, which is basically differential outputs. So again, that means output will be a combination of that will be the difference between the both these two terminals, V in one and V out one and V out two. But now I'm going to take a simple output, which is a single-ended output. Fine then. Now, because I'm going to use, let me just use the other marker, because I'm going to use the concept of potential divider. So I need to divide the potential initially. Let's do that. If this is 1.8, this would be 0.9, and here also would be 0.9. Now, because it's a 0.9, this particular node is connected in a diode connected format. So this also would be in the 0.9 volts. Okay. So just a moment, let me just open in the meantime the cadence. Okay, it's done. So let me just do that. Let me just open the cadence in the meantime. Okay, so these are the voltages that are getting divided. So because it is exactly divided between the VDD and the ground, so 0.9 volts will come out here. Now between here to here, this MOSFET is there. So that means there will be a 0.45 that will be divided over here. Yeah, so that's how I'm going to consider this entire thing. So that means these are the voltages that I have already said. Now it's time to, and one more thing is here, and the current which will be flowing over here would be IDD by 2. I can say it as IDD also, or ISS, because it is connected at the towards this source. It is connected to ground. It is sometimes also called by the name ISS, and it is all called by the name tail current. So this will be IDD by 2 over here. IDD by 2 currents that will be flowing over here. Okay, so now let's try to get into the design perspective. So this is my schematic which I'll be using. So if this is a schematic, so I need to design this particular amplifier with the given specifications. So what are the given specifications? So I'm going to do the design for a gain of 40 dB for a slew rate of, given slew rate is, slew rate should be ideally very high. Do remember that 5 volts per microsecond. That means the rate at which the output voltage changes. Now here that means for every 1 microsecond the output is changing at a rate of 5 volts. So that's basically the thing. And what is that it is going to indicate? It is basically you give the input at this particular instant, and you should see the output the very next instant. It should not happen that you give the input now and you see the output after 5 minutes. So that will be a lot of delay. So those kind of delays should be always avoided, and that's basically done with the help of that. That's basically controlled with the help of your slew rate. So that's basically how your slew rate thing is going to work. And then we have one more parameter that comes into picture, gain bandwidth. See why I took up this uh, simulation first rather than the theory, because here you'll try to understand the realistic view of this slew rate and where it is used. Hence you can quote, and hence you can answer the question when something is asked about slew rate, rather than mugging up the bookish definition. So if I just talk about in terms of theoretical aspect, it will be bookish definition that I'll be quoting. Here, how I'm going to use the slew rate, what is gain bandwidth, everything you'll be able to see that. So this will be 5 megahertz I'm going to take. Fine. So with all these things, let's try to design this. And when I try doing this, I'm going to assume L is equal to some 4 to 5 times the normal fix, which is my 500 nanometer. Okay. And also, if you see the previous things, if I just mark this point as node Y, and let me mark this as point X, and this is your V out. So if you see here, Vx is equal to V out. Always remember that. So because this is in a diode connected format, so whatever the VGS voltage that is present over here, which is now zero point 0.9, the same zero point 0.9 is applicable to this PMOS, and whatever the current that is flowing over here, the same current will be flowing over here. That means whatever outcome I'm going to see over here, the same outcome can be seen over here. That is the thing. And also we can see it's the same voltage, zero point 0.9 voltage is here and 0.9 voltage is dropping over here due to the potential division method. So this Vx is equal to V out in this case. And also I can say one more thing. There is a over V, which is over here, Vy is equal to 0.5. Now this is equal to 0.9 to 0.45. So that will help us for our design. Okay. So step one. So first I need to see, usually I took up everything with the help of the current. I started all my designs of the amplifiers by considering the current. And how did I consider the current? By using the power formula. From there I derived the current and I started. Here I'll not use the power number, rather IDD or ISS. Current equation is given by slew rate into load capacitance. So what is your slew rate now? It's 5 volts per microsecond. And what's your load capacitance? It is 10 picofarad. See how all these parameters will matter a lot when we try to get into the current. How did I say these are current only? If you see, this is in volts and this is in terms of capacitor, and current is nothing but the charge movement, which I can say Q. So is it not in the format of Q is equal to CV? If you see, right? Simple definition. Q is equal to CV, and if I want to express the charge in terms of current, it is basically dq by dt. The movement of charge per unit time is nothing but your current. So it all boils down to the same equation. That's how my current is equal to slew rate times the capacitance. So based on that, my drain current now would be equal to 50 microampere. That means whatever the width I'm going to consider, I'm going to consider it with respect to 50 microampere. Remember, in all our previous cases, we used to mark the current at 100 microampere because we got it as 100 microampere. Now here we will be marking it at 50 microampere. So once you mark the current at 50 microampere, you'll be able to get the results. So now let's go into the other step. So first consider M naught. How your M naught looks. Let's see here. This is the scenario where your source is grounded, drain is at 0.5 volt, and I need to find VG naught. So let's try to mark it. VG naught. This is M naught. So here it is 0.45. This is ground, and I'm going to apply the same formula. VG is equal to Vs plus Vt. And remember, you have already done the dummy DC analysis for an PMOS and NMOS, do consider that VT itself. So in this case, it is 0 Vs, VT is 200 milli, and 5% of VDD is 90 milli, and we got it as VG naught is 290 milli, which I'm going to approximate it to 300 milli. And when I sweep this with respect to ID versus W, we get W. So let's do that quickly. So in my case, I have already done that. Let me just open. So differential amplifier NMOS. So I have done it over here. Let me see what is that NMOS. Yeah. So it's the same circuit what I'm going to use over here. Look here. VG, this is grounded, and this is 0.5 volt, 0.45 volt. So grounded, this is 0.45 volt, that is 450 milli, and here I'm going to sweep the width as W, which is I have taken it over here, and my gate voltage is 300 milli. Let's try to save it, launch ADL. But this time I'll just show you what is going to happen if I sweep the width from, basically if I'll choose the DC analysis and I'm going to sweep the width from, let's first choose the MOSFET, sweep the 2 micro to 50 micro. Let's see what is going to happen. And the current to be plotted, outputs to be plotted is my current, which is my drain current. There you go. Done. So simple. Looks very simple when you start doing all the things. Okay, so I have done this entire thing. Now, if you sweep, now if you observe here, I think you're able to get it right. Yeah. So now I'm going to mark it to 50 micro. So what is, and I'll just come over here and I press marker M and I'll cue it and I'll change the position by X mode. I'll arrange it to 50 micro exactly. And I want to get it as 12.9 micro. So that means my first width, we get W is equal to 12.9 micrometer. So that's your W naught, which is basically for this. So here my W is okay. Now on the same line, let's try to get into the other thing. Now here the M0 transistor is an individual transistor, which is basically at the tail side here. So it doesn't share any relationship with the thing. But if I find out the width of M1, it will be equivalent to M2. And if I find the width of M3, it will be equivalent to M4. So that means now I'll just find what is for M1. So how is your M1 connected? M1 is basically is your NMOS. So here you have 9.9 volt, and here this is your 0.45, and this is you need to apply the formula. Sorry, let's try to do it here. For M1, so this is at 0.9 volt and this is at 0.5 volt, and let's try to apply a formula. Here VG1 is equal to, now what is Vs? It's 0.45 plus VT is 200 milli plus 5% of VDD is 90 nano. So if I do that, VG1, what is that I'm going to get? If I just calculate it, 450 plus 200, 290. That would be 450, 650, 740. Right? So 740 milli or 0.74. So once you find this hole, then again do the sweeping. Let's try to quickly do that. See, it is always very simple when you are acquainted with these kind of stuffs. So now this is also your NMOS. So I'll just change it here only. So what is that I want to fix up here? It should be 0.9 volt. That means 0.9 volt. And this is 0.74. That is 740 milli. And below you should have one more voltage source over here. So I'll just copy this. And that value should be equal to 0.45. That is 450 milli. There you go. And I'm going to sweep the W. So I saved it. ADL is anyhow launched. Because it's the same MOSFET you have chosen, it's already being launched over here. If you want to do it, you can do it once again. That's not an issue. And yeah, now let's try to sweep it, run it. W1. So I'm going to get it for W1. So horizontal marking, I'll change it to 50. And Q, change this to Y mode and fix it to 50. So I want to see the value as 15.16 micro. I'll just note it down. And once I did it over here, that means this is same for M1 and M2. So we get here W is equal to 15.16 micrometer. Yeah. Now the same line, let's quickly do it for M3. Why M3? Here is your M3. This one, M3 or M2. Anyway, anything is fine. Now here, let's try to take this one. So how is that it is connected? It is in this manner. It's a PMOS now. And both these are connected. Now look here, the advantage of this is both your VG is already connected to ground. So no need to consider that particular, calculate that VG like this formula. So it's already calculated. So I just need to sweep it. That's it. Nothing more than that. So I have all the voltages over here. So, but here I require the NMOS, sorry, PMOS. So I'll just load the PMOS, which I have already done that. So here is your diff amp PMOS. Yeah. Look here, is it not the same thing that it is going to look? It's your the VDD is at 1.8 and gate and source are shorted to 0.9. See, it's at 1.8 and gate and source are shorted to 0.9. And I'm sweeping the W, which I'm making it as a variable W. Let me just launch it. Copy from cell view. 2 micro analysis. DC operating points, component variable, select the components. Variable to be plotted would be W, which is capital W, which I have mentioned there. And I'm sweeping from 2 micro to 50 micro. Say OK. Save it once again. Come back to the ADL window. Outputs to be plotted. Select on the design. I can go back to the ADL window and I'll run it. There you go. Yeah. Now let's try to mark it. Now look here, it is the current is in terms of milli. Okay, let's see if I am able to get that 50 micro. See, now there is a glitch over here. Whatever the sweep you have done, that sweep is not at all enough to get the 50 microampere current because you're sweeping it from 2 micrometer of width to 50 micrometer of width. But the sweep variable, the current is coming even lesser than that. I'm not able to get the current on this graph. So what I'll do, I'll come back I'll change the initial sweep value to 0.5 micro, which is 500 nano, and then I'll change the sweep variables from again 0.5 micro to 50 micro. I'm just going to drag it one step behind because I'm not able to find the current and width intersection. So what I did, I just dragged it a little bit backward. Now I'm going to see whether I'm still able to get the issue solved or not. Yeah, now you go. Now that horizontal line is passing on this particular curve. So I'll just place a marker where it is exactly 50. I'll just move around the cursor until I see the 50 over here. And then I press M, and then I say Q. And there is always an option where you can change this value, marker value, to an exact value. Yeah, now you can see if I just let me just make it large. It's still not marking properly. So let me I'm just making it large so that I can, yeah, it is changed to 51. Now you can see it is 929 nano. So the M3 for M3 and M4, W is 923. What is that? 929. 929 nanometer. That's your total width. So this is how you're going to calculate the entire widths of all your MOSFET. The same way what we adopted in all our previous cases. Now once that is done, we can build the differential amplifier, diffamp. So let's try to create a new cell. Yeah, new cell creation, and basically I'm just going to leave this. So basically what is that I'm going to do? I'm going to do this entire thing diffamp design. I'm going to say it as. So in this design, I'm going to rig up the same circuit which I showed it over here by marking the appropriate values of W. And I'm going to give the respective gate voltages, which I have that also I have calculated. And then we'll try to run that particular thing and see how this is different than your other amplifiers. And before we run this, now I just want to have a discussion on the theory. So that I'll take up in the next session. So this rigging up, maybe you can try it at your end till this step, and then when I complete the theory session, we can collaborate with the results, practical scenario based result. So we can see how these results are going to be different than the other normal amplifier based thing. So just stop it now. So we can have the rest of the things continued in the next session. Stop the recording.